Good afternoon, everybody. Thanks for giving us the opportunity to present LUMIO mission. So I'm Fabio Ferrari. I'm a science lead for LUMIO. All right, so LUMIO is a CubeSat, a 12-view CubeSat from the European Space Agency with a huge support of ASI that is aimed at the second Lagrangian point of the Earth-Moon system. And that's the point behind the Moon from our perspective. So that's the point that's going to be facing all the time the lunar far side. And the broad goal is to observe, quantify, and characterize meteoroid impacts by detecting their impact flashes. So this is a short history of the mission. Since 2016 when it was proposed. Then it was funded by ESA through GSP and then GSTP. And now we are currently towards the end of phase B, which should conclude by September this year. So that's where we are, and that's where we would like to be in a few years. So the plan is to have phase C next year, and then ramping up to launch, which is now planned for 2027. So this is a short overview of the what it will do, the mission phases. So it will likely be on a custom transfer that was required. So for the dynamicist, this is a weak stability boundary transfer, and this was required to lower the delta V substantially at the cost of a longer transfer time. And in the end, we will reach this near rectilinear halo orbit around L2, where LUMIO will be operative for about 1 year. So a few more detail on the operative orbit. Since we are near the L2, we have this nice lunar far side coverage. So we will be always facing the far side of the Moon, and we will always have a full disk in our field of view for the camera, which is the main payload. Also, Earth will be always in sight because the size of the halo itself is larger than the Moon when seen from Earth, and the orbit of the period of the orbit is about 14 days. So we are in 2-to-1 resonance with the Earth-Moon system. All right, so a few more details here. Well, I can just pick the mass, which is about 26 kilos. And again, we are a 12U CubeSat. So still a small, but pretty, I would say, ambitious mission. So just a few words on the science part, which, of course, is concerned mainly on about impact flashes detection. So as we know, this is, let's say, the final part of a complex process, physical process involved in the meteoroid impacts on the surface. So where we have, of course, crater excavation, then some energy goes into seismic waves, some energy goes into ejecting particles off the surface, and some energy goes into radiation emission. That's what we actually see and detect. So there are examples of similar projects that have been run from Earth. So using ground-based observation, and Neliota is a great example for this, and gives us the idea of what our, let's say, science product will be like. So this image that you see here is from the Neliota project, which again observes the Moon from Earth and looks for impact flashes. So you might wonder then, why, if we have these wonderful programs, do we want to get into space? And I would say there are a few, let's say, valid reasons for that. And I would start from mentioning that ground-based observations are somehow limited. Of course, they are possible during the Earth night and only when the moon is not, of course, fully illuminated. So within just a range and within the overall month. So only some geometric position are possible, and there is no possibility for a full disk actually detection. Also, the measure is going to be affected by earth shine that you always have, and it's of course constrained by weather and by atmosphere. So you don't have this, of course, when you go into space, and also you don't have this when you go into L2. So you don't have earth shine, of course, because you are in the far side, and you can have uninterrupted observations, which means basically 15 days, the nighttime of the moon, where you actually see the night side from the far side of the moon. All right, so no earth shine, higher quality in principle science products. And this is very nice to complement, of course, the ground-based observations that we have. So this is a estimate in terms of energy of what we LUMIO could observe. So the red and yellow points that you see here. So we estimate to detect objects in the range of 10 to minus 6, 10 to minus 1 kiloton. And this fits nicely actually with the current literature. Looks like it's filling some kind of void that we have. Okay, so this curve is based on Earth measurements, but we can have similar thing on as well, since let's say the meteoroid environment is not going to be very different from a dynamical point of view. So in order to tackle all these tasks and also to extend it a little bit, we have started to set up a science team. This actually just started, so we have issued a call for about that earlier this year, and we just kicked off the activities and have we'll have the first science team meetings in 2 weeks from now. So apart from the, let's say, main mission objectives, we would like to extend it to the community and to synergies with other missions, other projects, gathering all the information and putting them together to see whether we can constrain meteoroid properties, surface properties, impact properties, and characterization of the impact process, and so on. So I conclude with just acknowledging the consortium and partners of this initiative, and that's it from my side. Thanks.